Every decision creates a universe. Every quantum event births reality. Right now, as you listen to these words, countless versions of you exist across infinite worlds. In one universe, you chose to listen to music instead. In another, you decided to go for a walk. In yet another reality, the very atoms that compose your body arranged themselves differently, creating a you that made completely different choices throughout life. This isn't poetry or imagination. This is the many worlds interpretation of quantum mechanics, one of the most profound and startling theories in all of science. From Whispering Universes channel, where scientific wonder meets gentle contemplation, we invite you on a journey through the quantum multiverse that surrounds and encompasses every moment of your existence. The story begins in the early 1900s, when physicists first discovered that the universe behaves in ways that defy every intuition about reality. Matter exists in multiple states simultaneously. Particles tunnel through barriers they shouldn't be able to cross. The very act of observation changes the nature of what we observe. These discoveries led to quantum mechanics, the most successful theory in the history of science, yet also the most mysterious. But quantum mechanics presented a profound puzzle. If particles can exist in multiple states at once, why do we only ever observe them in single, definite states? Why does the quantum world of infinite possibilities collapse into the classical world of definite outcomes? The traditional answer involves something called wave function collapse, the idea that measurement somehow forces reality to choose one possibility from many. Yet in 1957, a young graduate student named Hugh Everett III proposed a radical alternative. What if the wave function never collapses? What if every possible outcome of every quantum event actually occurs, but in separate, parallel universes? What if reality doesn't choose, but instead splits, creating new worlds to accommodate every possibility? This is the many worlds interpretation, and it suggests that you are living in just one branch of an infinite tree of reality. Every quantum measurement that has ever occurred has split the universe into multiple copies, each containing a slightly different version of history. The you that exists in this universe is just one of countless versions, each experiencing their own unique timeline through the quantum multiverse. Tonight, we'll explore this extraordinary theory and its implications for your understanding of existence. We'll journey through the quantum experiments that revealed reality's strange behavior, meet the brilliant minds who dared to imagine infinite worlds, and discover how modern technology is beginning to provide evidence for this mind-bending theory. We'll examine what it means to have infinite versions of yourself scattered across parallel realities, explore how quantum computers might be borrowing computational power from other worlds, and contemplate the profound questions that arise when every possible history unfolds simultaneously across the multiverse. So settle into this moment, this particular branch of reality, and let your consciousness drift gently across the infinite landscape of parallel worlds. In some universe, you're already asleep and dreaming. In another, you're wide awake and fascinated. In this one, you're somewhere beautifully in between, ready to explore the quantum multiverse, where every possibility becomes reality somewhere in the vast expanse of existence. Our journey into parallel worlds begins with one of the most beautiful and disturbing experiments in all of physics, the double-slit experiment. First performed by Thomas Young in the early 1800s, this simple setup would eventually shatter every assumption about the nature of reality and point toward the existence of infinite parallel worlds. Picture a barrier with two narrow slits cut into it, like two doorways side by side. When you shine light through these slits onto a screen behind the barrier, something magical happens. Instead of seeing two bright lines corresponding to the slits, you see a pattern of alternating light and dark bands, an interference pattern that can only arise when waves overlap and either reinforce or cancel each other out. This made perfect sense when scientists thought of light as a wave. Waves passing through both slits would interfere with each other, creating the observed pattern. But in the early 1900s, physicists discovered that light also behaves like particles, called photons. This created a puzzling question: how can particles create wave-like interference patterns? The mystery deepened when scientists performed the experiment with individual photons, sending them one at a time through the slits. Logic suggests that each photon must travel through either one slit or the other, never both. Yet amazingly, the interference pattern still appeared, even though only one photon passed through the apparatus at a time. Each single photon somehow interfered with itself, as if it had traveled through both slits simultaneously. But here's where reality becomes truly strange. When scientists placed detectors at the slits to determine which path each photon actually took, the interference pattern vanished completely. The mere act of observation changed the photon's behavior from wave-like to particle-like. It was as if the photon knew whether it was being watched and behaved accordingly. John Wheeler, the brilliant physicist who coined the term black hole, pushed this strangeness even further with his delayed choice experiment. He showed that you could decide whether to observe the photon's path after it had already passed through the slits, but before it reached the screen. Somehow, your future decision about whether to observe retroactively determined whether the photon had behaved like a wave or particle in the past. Quantum erasure experiments revealed even more bizarre behavior. Scientists could make the interference pattern appear and disappear by manipulating information about the photon's path, even without directly observing the photon itself. It seemed that information itself, not just observation, played a fundamental role in determining reality. These experiments revealed that particles exist in superposition, simultaneously exploring all possible paths until measurement forces them to choose a single trajectory. But this raises the profound question that would eventually lead to the many worlds interpretation. What constitutes a measurement, and why does it seem to collapse the wave function into a single reality? The traditional Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggested that measurement causes the wave function to collapse randomly into one of its possible states. But this explanation felt unsatisfying to many physicists. It required accepting that reality itself was fundamentally random and discontinuous, with measurements causing sudden, inexplicable jumps from quantum superposition to classical definiteness. The double-slit experiment thus became a window into the quantum world's deepest mystery. It showed that particles have no definite properties until measured, that observation affects reality, and that the quantum world operates according to rules completely unlike our everyday experience. Most importantly, it revealed that nature somehow allows for multiple contradictory possibilities to coexist until measurement forces a single outcome. This bizarre behavior of quantum particles at the smallest scales would eventually lead young Hugh Everett III to propose the most radical solution imaginable. What if measurement doesn't force reality to choose at all? What if every possible outcome actually occurs, but in separate, parallel universes that we simply can't perceive? As you drift towards sleep tonight, imagine every photon in your room exploring multiple paths simultaneously, every particle in your body existing in quantum superposition until the universe splits to accommodate all possibilities. In the gentle darkness, let your mind contemplate this strange quantum world where reality itself seems to depend on consciousness and observation. In 1935, Erwin Schrödinger crafted what would become the most famous thought experiment in physics, a story that perfectly captured the absurd implications of quantum mechanics when applied to the everyday world. His imaginary cat would eventually help lead science toward the revolutionary idea of parallel universes. Schrödinger was deeply troubled by the Copenhagen interpretation of quantum mechanics, which suggested that particles exist in superposition until measured. He wondered, if this is true for particles, why don't we see superposition in the macroscopic world? To illustrate this paradox, he devised a diabolical scenario that would amplify quantum weirdness to visible scale. Imagine a sealed box containing a cat, a Geiger counter, a radioactive atom, a hammer, and a flask of poison. The radioactive atom has a 50% chance of decaying within an hour. If it decays, the Geiger counter detects the radiation and triggers the hammer to break the flask, releasing poison that kills the cat. If the atom doesn't decay, the cat lives. According to quantum mechanics, before measurement, the radioactive atom exists in superposition, both decayed and not decayed simultaneously. This means the entire system, including the cat, must also be in superposition. Until someone opens the box to observe the outcome, the cat is both alive and dead at the same time. This conclusion struck Schrödinger as ridiculous. How could a cat be simultaneously alive and dead? Yet this is exactly what quantum mechanics seemed to predict when its rules were consistently applied to larger systems. The thought experiment revealed a fundamental problem. The theory that worked perfectly for individual particles seemed to lead to absurd conclusions when extended to familiar objects. The Copenhagen interpretation handled this by suggesting that measurement causes wave function collapse. The moment someone opens the box, the superposition breaks down, and reality chooses whether the cat is alive or dead. But this solution raised even deeper questions. What exactly constitutes a measurement? Why does observation have such power over reality? At what point does the quantum world transition into the classical world we experience? Einstein, Schrödinger's contemporary and friend, was equally disturbed by these implications. He famously declared that God does not play dice with the universe, expressing his belief that reality must be deterministic rather than fundamentally random. In 1935, Einstein, Podolsky, and Rosen published a paper arguing that quantum mechanics must be incomplete because it led to what Einstein called spooky action at a distance. Their EPR paper described entangled particles that seemed to instantaneously affect each other across vast distances. Einstein believed this showed that quantum particles must have hidden variables, predetermined properties that we simply couldn't measure. He thought quantum mechanics' randomness was merely a reflection of our ignorance, not a fundamental feature of reality. Decades later, John Bell would prove that Einstein was wrong. Bell's theorem, published in 1964, showed that no theory based on hidden variables could reproduce all of quantum mechanics' predictions. Experiments have since confirmed that quantum entanglement really does involve instantaneous correlations across space, even though no information travels faster than light. But Schrödinger's cat remained stubbornly paradoxical. The thought experiment highlighted what became known as the measurement problem, the mysterious transition between quantum possibility and classical actuality. Why do we never see macroscopic superpositions? Why does measurement seem to force reality into a single state? Various interpretations emerged to address this puzzle. The Copenhagen interpretation insisted that measurement causes genuine wave function collapse, but couldn't explain what constitutes measurement or why it has such power. Hidden variable theories attempted to restore determinism, but were ruled out by Bell's theorem and subsequent experiments. Some physicists propose that consciousness itself plays a special role in causing measurement, but this seemed to grant minds impossible power over physical reality. Others suggested that decoherence interaction with the environment gradually destroys superposition, but this still couldn't explain why we experience only one outcome rather than all of them. The measurement problem seemed intractable until a young graduate student named Hugh Everett III proposed the most radical solution imaginable. What if Schrödinger's cat really is both alive and dead, but in different universes? What if measurement doesn't collapse the wave function, but instead causes reality to split into multiple branches, each containing one possible outcome? In Everett's interpretation, when you open the box, the universe divides. In one branch, you find a living cat. In another, identical branch, another version of you discovers a dead cat. Both outcomes actually occur, but each version of you can only experience one branch of reality. This solution preserved quantum mechanics' mathematical structure while eliminating the mysterious collapse postulate. The wave function continues evolving, according to Schrödinger's equation, in all branches simultaneously. Superposition never disappears, it just becomes distributed across parallel worlds that can't interact with each other. As you rest in the quiet darkness tonight, consider the possibility that countless versions of Schrödinger's cat exist across the multiverse, some alive, some dead, some in states we can barely imagine. Perhaps consciousness itself is quantum mechanical, branching along with physical reality into infinite parallel streams of experience. In the spring of 1954, a 24-year-old graduate student at Princeton University began developing what would become the most radical theory in physics. Hugh Everett III was working on his doctoral thesis under John Wheeler's supervision, grappling with the measurement problem that had puzzled physicists for decades. His solution would be so revolutionary that it took the physics community 20 years to take it seriously. Everett was a brilliant, unconventional thinker who approached physics with mathematical rigor and philosophical boldness. Unlike many of his peers who were content to "Shut up and calculate," as physicist David Mermin would later phrase it. Everett wanted to understand what quantum mechanics really meant. He was particularly troubled by the Copenhagen interpretation's reliance on wave function collapse, a process that seemed to violate the very mathematical structure of quantum theory. The young physicist noticed something profound. Schrödinger's equation, which describes how quantum systems evolve over time, is completely deterministic and reversible. Nothing in the equation suggests that wave functions should randomly collapse during measurement. The mathematics of quantum mechanics actually predicted continuous, branching evolution, not sudden jumps to single outcomes. Everett proposed taking the mathematics literally. Instead of assuming that measurement causes collapse, he suggested that measurement causes the universal wave function to branch into multiple copies, each containing a different outcome. The observer becomes entangled with the system being measured, creating separate branches of reality for each possible result. In his 1957 doctoral thesis, titled "The Theory of the Universal Wave Function," Everett outlined this revolutionary interpretation. He argued that reality consists of a constantly branching tree of universes, with new branches forming whenever quantum measurements occur. Every possible outcome of every quantum event actually happens, but in separate, non-communicating branches of the universal wave function. This meant that measurement doesn't destroy superposition, but rather distributes it across parallel worlds. Each branch contains an observer who experiences only one outcome, even though all outcomes occur simultaneously across the full multiverse. From any individual observer's perspective, measurement appears to cause random collapse, but from the universal perspective, everything that can happen does happen. Everett's interpretation solved the measurement problem elegantly. There was no need for mysterious collapse mechanisms or special roles for consciousness. Quantum mechanics could be applied consistently at all scales, from individual particles to entire universes. The theory's mathematical structure remained pure and unmodified. However, Everett's advisor, John Wheeler, had mixed feelings about the radical implications. Wheeler recognized the mathematical elegance, but worried about the theory's philosophical consequences. He encouraged Everett to tone down the more provocative aspects when presenting the work publicly. Wheeler himself alternated between supporting and distancing himself from the interpretation throughout his career. The broader physics community reacted with skepticism and often hostility. Niels Bohr, the father of the Copenhagen interpretation, visited Princeton in 1959, but showed little interest in Everett's ideas. Most physicists were comfortable with the Copenhagen interpretation's practical success and saw no need for Everett's many worlds complications. Faced with professional isolation and lack of support, Everett left academic physics after receiving his doctorate. He joined the Pentagon's Weapons Systems Evaluation Group, where he worked on nuclear strategy and game theory. He developed important mathematical tools for analyzing warfare scenarios, ironically using his skills to contemplate potential futures rather than parallel realities. For nearly 2 decades, Everett's interpretation remained largely ignored by the physics community. Only a handful of physicists, including Bryce DeWitt and Neil Graham, kept the idea alive. DeWitt coined the term many worlds interpretation and helped popularize Everett's ideas through conferences and publications in the 1970s. The interpretation began gaining serious attention as physicists became more concerned with quantum mechanics' conceptual foundations. The development of quantum field theory and cosmology raised questions that the Copenhagen interpretation couldn't easily address. How could measurement occur in the early universe before observers existed? How should quantum mechanics be applied to the universe as a whole? Everett's interpretation provided natural answers to these questions. The universe could evolve quantum mechanically from the beginning, with branching occurring automatically whenever quantum systems became sufficiently complex and entangled. No external observers were required. The universe could measure itself through internal interactions. Modern developments have lent increasing support to Everett's vision. Decoherence theory, developed in the 1980s and 1990s, showed how quantum systems naturally evolve toward effectively classical behavior through environmental interaction. This helped explain why we don't typically observe superposition at macroscopic scales, not because of collapse, but because decoherence rapidly separates different branches into non-interfering components. Computer simulations have demonstrated how classical behavior emerges from quantum evolution in complex systems. Quantum error correction research has revealed how information can be preserved and isolated in quantum systems. These developments support the idea that branching occurs naturally as quantum systems become more complex and entangled. Today, the many worlds interpretation is considered one of the major approaches to understanding quantum mechanics, alongside the Copenhagen interpretation, hidden variable theories, and objective collapse models. Many leading physicists, including David Deutsch, Max Tegmark, and Sean Carroll, advocate for the many worlds approach. Everett died in 1982 at age 51, just as his ideas were beginning to gain widespread recognition. He never lived to see quantum computers vindicate his vision of parallel computation across multiple realities, nor did he witness the growing acceptance of his radical solution to quantum mechanics' deepest puzzle. As consciousness settles into the quantum realm tonight, imagine the young Everett discovering that reality branches with every observation, that you exist in countless parallel versions across the ever-expanding tree of possibilities. In his mathematics, every potential future becomes actual, somewhere in the infinite landscape of the multiverse. To understand how infinite parallel worlds could arise from quantum mechanics, we must delve into the mathematical heart of Everett's vision. The mathematics reveals a universe far stranger and more beautiful than our everyday experience, suggests a reality where infinite possibilities unfold simultaneously across vast networks of parallel branches. The foundation of many worlds theory rests on the universal wave function, a mathematical description of every quantum system in the universe as a single, evolving entity. Unlike the Copenhagen interpretation, which treats measurement as fundamentally different from ordinary quantum evolution, Everett's approach applies quantum mechanics universally, without exception or modification. In quantum mechanics, the state of any system is described by a wave function that exists in an abstract mathematical space called Hilbert space. This infinite dimensional space contains every possible configuration the system could occupy. For a simple particle, the wave function might specify the probability of finding it at various locations. For complex systems, the wave function becomes vastly more intricate, encoding correlations and entanglements between countless components. When quantum systems interact, such as when a measuring device encounters a particle in superposition, their wave functions become entangled. The mathematics shows that this entanglement naturally creates separate branches in the combined wave function, each corresponding to a different measurement outcome. These branches evolve independently, following the deterministic Schrödinger equation without any need for random collapse. Decoherence theory, developed by Wojciech Zurek, Eric Juice, and others in the 1980s and 1990s, revealed the mathematical mechanism behind branching. When a quantum system interacts with its environment, as all macroscopic systems inevitably do, the environment rapidly becomes entangled with the system in ways that distinguish different outcomes. This environmental entanglement spreads information about the system throughout countless environmental degrees of freedom, making it effectively impossible for different branches to interfere with each other. The branches become decoherent, mathematically separate, and practically independent, even though they remain part of the same universal wave function. The mathematics predicts that decoherence occurs extremely rapidly for macroscopic systems. For a dust grain floating in air, environmental interactions destroy quantum coherence in less than a billionth of a second. For larger objects like cats or humans, decoherence happens almost instantaneously. This explains why we never observe macroscopic superpositions, not because they don't exist, but because decoherence immediately separates them into non-interfering branches. Probability emerges naturally from the many worlds framework through what's called the Born rule. The mathematical structure of quantum mechanics shows that the amplitude of each branch determines the probability of finding yourself in that particular reality. Branches with higher amplitudes are more likely to contain your future observations, while lower amplitude branches become increasingly unlikely. This probabilistic structure arises from the squared amplitudes of the wave function components, just as in standard quantum mechanics. However, instead of representing chances of collapse to specific outcomes, these probabilities indicate the relative frequencies of different branches, across the vast landscape of parallel realities. David Deutsch's work on quantum computation revealed another crucial aspect of the mathematics. Quantum computers achieve their power by performing calculations across multiple branches of the multiverse simultaneously. When a quantum computer factors a large number using Shor's algorithm, it essentially borrows computational resources from parallel versions of itself, with each branch exploring different potential factors. This suggests that the parallel worlds of many worlds theory are not merely abstract mathematical constructs, but have genuine physical reality. The computational speedups achieved by quantum computers require massive parallel processing that can only be explained if the calculations are actually occurring across multiple realities. The mathematics also addresses one of the most common objections to many worlds theory, the apparent violation of energy conservation. If new universes are constantly being created, where does the energy come from? The answer lies in the fact that the universal wave function conserves probability, not classical energy. Each branching event redistributes the total probability amplitude across the new branches without creating additional energy within any individual branch. Modern research has extended the mathematical framework to include quantum field theory and cosmology. The mathematics shows how quantum fluctuations in the early universe could have created the branching structure that produced our observable cosmos. Eternal inflation models suggest that branching occurs not just at microscopic scales, but at cosmic scales, creating bubble universes with different physical laws and constants. String theory's landscape of possible vacuum states provides another mathematical framework for understanding parallel realities. The theory suggests that different branches might settle into different vacuum configurations, leading to universes with varying numbers of dimensions, different fundamental forces, and altered physical constants. Information theory has also contributed to the mathematical understanding of many worlds. The framework shows how information about quantum measurements becomes distributed across environmental degrees of freedom, making it impossible to retrieve complete information about other branches from within any single branch. This mathematical structure explains why parallel worlds can't communicate with each other despite being parts of the same universal wave function. Once decoherence occurs, the information needed to demonstrate interference between branches becomes permanently scrambled throughout the environment, creating effectively classical behavior within each branch. The mathematics of many worlds thus presents a picture of reality as an ever-branching tree of possibilities, with each branch containing observers who experience a single, classical-seeming world. The deterministic evolution of the universal wave function creates the illusion of randomness from each observer's limited perspective, while maintaining perfect mathematical consistency across all scales and interactions. As you settle into rest tonight, let your mind drift through this mathematical landscape where every quantum event creates new branches of reality. In the gentle mathematics of the multiverse, consciousness itself becomes a wave function, exploring infinite possibilities across the vast network of parallel worlds, each carrying its own unique perspective on the one universal truth. In this quiet moment, as you listen to these words, countless versions of yourself exist across the branching multiverse. Some are nearly identical to you, differing only by a few quantum events. Others have diverged dramatically, shaped by different choices and chance encounters across parallel timelines. Tonight, we explore what it means to be one consciousness among infinite selves. The many worlds interpretation suggests that every quantum measurement creates new branches of reality, each containing a slightly different version of you. These parallel selves share your history up to the point of branching, but experience different outcomes from that moment forward. The quantum events that separate you from your other selves occur trillions of times per second, creating an ever-expanding tree of parallel lives. Consider a simple example: the radioactive decay of a single atom in your body. In this universe, the atom decays at a particular moment. But in a parallel branch, it decays slightly earlier or later. This tiny difference cascades through the complex chemistry of your neural networks, potentially affecting your thoughts, decisions, and experiences in subtle but meaningful ways. Most of your parallel selves are nearly indistinguishable from you. The vast majority of quantum events have negligible effects on macroscopic systems like your brain and body. These nearby branches contain versions of you experiencing essentially the same life, with differences so minute that you would consider them the same person if you could somehow meet them. However, as we trace backward through increasingly distant branches, the differences become more pronounced. Some parallel versions of you made different career choices, moved to different cities, or formed different relationships. These divergences often stem from quantum events that influenced key moments of decision-making in subtle ways. The butterfly effect amplifies small quantum differences into large-scale changes over time. A quantum event affecting a single neuron during a crucial decision might determine whether you accept a job offer, take a different route home, or strike up a conversation with a stranger. These seemingly minor variations can reshape entire life trajectories across parallel branches. Some branches contain versions of you living in dramatically different circumstances. In universes where key historical events unfolded differently perhaps, because quantum events influence the outcomes of crucial battles, discoveries, or political decisions, you might find yourself in unfamiliar social structures, technological landscapes, or even different geographical environments. The most distant branches might contain versions of you that are barely recognizable as the same person. If quantum events had influenced your parents' meeting, your conception, or early developmental processes, these alternate selves might have different personalities, talents, or even physical characteristics, while still sharing the same fundamental quantum origin point. This raises profound questions about personal identity across parallel worlds. What makes you, you, if countless versions exist with different experiences, memories, and characteristics? Most philosophers and physicists working on many worlds theory suggest that each branch contains a distinct but equally valid version of your consciousness, each experiencing their own unique stream of reality. The branching process means that you can never communicate with or directly observe your other selves. Once decoherence separates the branches, they become permanently isolated from each other. The environmental entanglement that creates distinct realities also prevents any possibility of inter-branch communication or travel. This isolation raises interesting questions about care and responsibility across the multiverse. Should you feel concern for your parallel selves? Some philosophers argue that since each branch contains genuine experiences and suffering, the welfare of all your versions matters morally. Others contend that you can only be responsible for choices within your own branch of reality. The existence of parallel selves also provides a unique perspective on regret and missed opportunities. Every path not taken in your life was taken by another version of you in a parallel branch. While you might wonder, what if, about different choices, rest assured that somewhere in the multiverse, another version of you explored that alternative path. This doesn't diminish the importance of your choices in this branch, however. The decisions you make determine which version of yourself you become within this particular reality. Your experiences, relationships, and accomplishments remain meaningful and valuable, even if other versions of you experience different outcomes. Some physicists have speculated about the subjective experience of branching. You never directly observe the moment when your branch splits from others, because each resulting version believes they experienced a continuous, uninterrupted timeline. The branching happens between conscious moments in the quantum realm below the threshold of direct experience. Yet the mathematics suggests that you are constantly becoming entangled with your environment in ways that determine which branch of reality you experience. Every photon that hits your retina, every molecule that binds to receptors in your brain, every quantum event in your neural networks contributes to the ongoing process of branch selection. From your subjective perspective, you experience a single, coherent timeline. But from the universal perspective, your consciousness exists as a branching structure, with each moment creating new versions that experience slightly different subsequent realities. You are not just one person, but an entire family tree of parallel selves, all equally real and valid. The anthropic principle suggests that you naturally find yourself in a branch compatible with your existence and consciousness. Branches where quantum events prevented your birth, survival, or development of consciousness contain no version of you to observe them. This selection effect might explain why your particular reality seems so remarkably fine-tuned for life and consciousness. As you drift towards sleep tonight, imagine your consciousness as part of this vast branching structure. With every breath, every heartbeat, every neural impulse, quantum events guide you along one path through the infinite maze of parallel possibilities. Your other selves dream different dreams in their own realities, each one a unique exploration of what it means to be conscious in the quantum multiverse. In the gentle darkness, let go of the boundaries that seem to separate you from your infinite family of parallel selves. Somewhere in the vast expanse of the multiverse, every version of your story unfolds, each one a precious thread in the cosmic tapestry of consciousness, exploring its own infinite nature. In the shadowed corners of many worlds, theory lies one of physics' most disturbing thought experiments. Quantum suicide, first proposed by cosmologist Max Tegmark in the 1990s, explores the darker implications of infinite parallel realities and reveals why some scientists prefer not to think too deeply about the multiverse's implications for consciousness and mortality. The scenario is deceptively simple yet profoundly unsettling. Imagine a quantum version of Russian roulette using a gun connected to a quantum random number generator. Each time you pull the trigger, the device measures the spin of an electron. If the spin is up, the gun fires. If down, it clicks harmlessly. According to many worlds theory, each trigger pull creates two branches, one where you die, another where you survive. From an external observer's perspective, this quantum roulette behaves normally. After many trigger pulls, most branches contain your death, with only a tiny fraction containing your survival. Any observer watching the experiment would almost certainly see you die, just as probability theory predicts. But here's where the thought experiment becomes disturbing. From your subjective perspective, you can only experience branches where you remain conscious. The branches where you die contain no awareness to experience death. This means that no matter how many times you pull the trigger, you always find yourself in the minority of branches where the gun didn't fire. From your internal viewpoint, the quantum gun appears to malfunction. It never kills you, despite the overwhelming odds. You might conclude that the device is broken, or that you're somehow protected by supernatural forces. But the real explanation is that consciousness can only observe branches compatible with its own continued existence. This suggests a horrifying possibility. If many worlds theory is correct, you might be functionally immortal from your own perspective. Every moment that could potentially end your life creates branches where you die and branches where you survive through increasingly improbable circumstances. Your consciousness automatically selects the survival branches, creating the subjective experience of immortality through quantum selection. Max Tegmark emphasized that he wasn't advocating for actual quantum suicide experiments. The thought experiment serves as a philosophical probe to explore many worlds theory's implications, not as a practical procedure. Real-world suicide attempts would likely succeed in most branches, and no one should test these ideas experimentally. The quantum suicide scenario reveals deeper issues about probability and subjective experience in the multiverse. Traditional probability theory predicts outcomes from an external, objective perspective. But if consciousness can only observe certain branches of reality, subjective probabilities might differ dramatically from objective ones. This creates what philosophers call the anthropic selection effect. Conscious observers naturally find themselves in branches compatible with their existence and awareness. This selection bias might explain many apparent coincidences about our universe's properties. We observe a cosmos fine-tuned for life, not because it was designed that way, but because we can only exist in branches where the physical constants permit consciousness. The quantum suicide argument extends to natural death and aging. If consciousness always selects branches where it continues to exist, why do we observe aging and death in our own timeline? Several possible explanations have been proposed, each raising its own philosophical puzzles. One possibility is that consciousness has natural limits. Perhaps the brain's information processing capacity or the body's biological systems set boundaries on how long awareness can persist, even across parallel branches. In this view, quantum selection can postpone death but cannot prevent it indefinitely. Another explanation involves the measure problem in many worlds theory. The mathematical amplitude of survival branches decreases exponentially with time and circumstance. Even if survival branches always exist, They might become so low amplitude that the probability of finding yourself in them approaches zero. Some theorists have proposed that consciousness itself might be quantum mechanical, with its own decoherence timescales. If awareness requires quantum coherence across neural networks, environmental decoherence might naturally limit how long consciousness can persist in any single branch, regardless of the body's physical state. The quantum suicide paradox also raises questions about personal identity across branches. If you survive improbable circumstances through quantum selection, are you the same person who began the experiment? Each survival event might require increasingly unusual brain states or environmental conditions, gradually transforming your identity in ways you don't recognize. These considerations have led some physicists to avoid thinking about many worlds theory's implications for consciousness and mortality. The scenarios become so strange and counterintuitive that they seem to push beyond the boundaries of meaningful scientific discourse into pure philosophical speculation. However, other researchers argue that these thought experiments reveal important aspects of consciousness's relationship to physical reality. If many worlds theory is correct, our subjective experience of probability, mortality, and identity might differ fundamentally from naive expectations based on single universe thinking. The anthropic principle suggests that conscious observers necessarily find themselves in universes compatible with consciousness, regardless of how improbable such universes might be objectively. This selection effect could explain many features of our cosmos that otherwise seem remarkably fine-tuned or coincidental. Some philosophers have extended the quantum suicide argument to collective consciousness and civilization. If technological civilizations can only observe branches where they avoid self-destruction, we might expect to find ourselves in timelines where humanity successfully navigates existential risks like nuclear war, climate change, or artificial intelligence development. These ideas remain highly speculative and controversial. Many physicists prefer to focus on testable predictions rather than exploring the multiverse's philosophical implications. The quantum suicide thought experiment serves primarily as a tool for understanding how consciousness might interact with branching realities, not as a guide for practical decisions. As you rest in the quiet darkness tonight, contemplate the strange comfort and unease of these ideas. If consciousness really does select branches where it persists, then every moment of your awareness represents survival through countless quantum branches that led to different outcomes. Your existence itself becomes evidence of improbable quantum paths through the infinite maze of parallel possibilities. Let these thoughts settle gently into sleep, knowing that tomorrow you will wake in whichever branch allows your consciousness to continue its exploration of reality. In the quantum multiverse, awareness itself becomes the compass, guiding you through infinite possibilities toward whatever strange and wonderful futures await in the branches where consciousness persists. Beyond the laboratory scale, where quantum mechanics was first discovered, lies a cosmos where quantum principles operate on the grandest scales imaginable. The quantum multiverse extends far beyond parallel Earths to encompass infinite variations of entire universes, each with potentially different physical laws, fundamental constants, and cosmic histories. Cosmic inflation, developed by Alan Guth, Andre Linde, and others in the 1980s, describes the universe's exponential expansion during its first fraction of a second. This inflationary period stretched quantum fluctuations in space-time to cosmic scales, creating the density variations that eventually became galaxies and stars. But inflation theory also suggests something far more radical. Our observable universe might be just one bubble in an eternal process, creating infinite cosmic realms. Eternal inflation models predict that the inflationary process never completely stops. While inflation ended in our region of space-time, it continues elsewhere, constantly creating new bubble universes within an ever-expanding cosmic multiverse. Each bubble begins its own Big Bang, developing into a separate universe with its own space and time. Quantum mechanics plays a crucial role in this cosmic branching. Quantum fluctuations during inflation determine not only the density patterns within each bubble universe, but also the fundamental properties that govern each cosmos. Different regions of the multiverse might undergo phase transitions that select different vacuum states, leading to universes with varying numbers of dimensions, different fundamental forces, or altered physical constants. String theory provides a framework for understanding how dramatically different these parallel universes might be. The theory's landscape of possible vacuum states contains roughly 500 different configurations, each potentially giving rise to a universe with unique physical laws. Some might have no electromagnetic force, others could have different numbers of spatial dimensions, and still others might lack the conditions necessary for matter to form at all. This vast landscape of possibilities addresses the fine-tuning problem that has puzzled cosmologists for decades. Our universe appears remarkably well-suited for life, with physical constants that seem precisely calibrated to allow stars, planets, and chemistry to exist. If any of several fundamental parameters were even slightly different, our cosmos would be sterile and lifeless. The quantum multiverse provides a natural explanation for this apparent fine-tuning. If infinite universes exist with all possible combinations of physical laws and constants, then some universes will inevitably have properties suitable for life and consciousness. We naturally find ourselves in one of these life-permitting regions, not because our universe was designed, but because consciousness can only arise in branches where the physical conditions allow it. This anthropic reasoning extends the quantum suicide argument from individual consciousness to cosmic consciousness. Just as your awareness selects branches where you survive, conscious civilizations can only observe universes where consciousness is possible. The seemingly improbable fine-tuning of our cosmos becomes inevitable from the perspective of conscious observers within the multiverse. However, the quantum multiverse raises profound questions about probability and prediction. If every possible universe exists somewhere in the multiverse, how can we make meaningful scientific predictions? Why should we expect our universe to have typical properties rather than bizarre, unique characteristics? These problems have led to the development of measure theory in cosmology mathematical frameworks for comparing probabilities across infinite collections of universes. Different measures can lead to dramatically different predictions about what kinds of universes conscious observers should expect to find themselves inhabiting. Some measures predict that most conscious observers should find themselves in universes that are just barely suitable for consciousness, with physical constants precisely at the boundary values needed for stars and chemistry. Others suggest that typical observers should inhabit universes with abundant life and optimal conditions for consciousness development. The eternal inflation scenario also connects to many worlds' quantum mechanics in subtle ways. The quantum branching that creates parallel versions of you might be related to the cosmic branching that creates parallel universes. Each quantum measurement in your brain might correlate with bubble universe formation at cosmic scales, linking personal consciousness to cosmic evolution. Recent observations in cosmology have provided some evidence supporting multiverse theories. The cosmic microwave background radiation shows patterns consistent with eternal inflation models. Some researchers have claimed to detect signatures of bubble universe collisions in the cosmic microwave background, though these claims remain controversial. Dark energy, the mysterious force causing our universe's accelerated expansion, might also connect to multiverse cosmology. String theory suggests that dark energy's value should vary across different regions of the multiverse. Our universe's particular value might be selected by the anthropic requirement that galaxies and stars have enough time to form before expansion tears everything apart. The possibility of cyclic cosmologies adds another layer to multiverse models. Some theories suggest that universes undergo repeated cycles of expansion, contraction, and rebirth. Each cycle might select different physical laws through quantum processes, creating an eternal sequence of cosmic reincarnations, exploring different possibilities. These cosmological extensions of quantum mechanics blur the traditional boundaries between physics and philosophy. If infinite universes exist with all possible physical laws, what does it mean to discover the laws of nature? Are we uncovering universal truths, or merely documenting the particular configuration that allows our existence? The quantum multiverse also raises questions about the ultimate fate of consciousness. If bubble universes can have arbitrarily long lifespans and different physical laws, that might consciousness persist in forms we cannot currently imagine? Could awareness eventually spread throughout the multiverse, experiencing every possible reality? Some theorists have speculated about the possibility of communication or travel between bubble universes. While the enormous distances and different physical laws make such interactions highly improbable, the infinite size of the multiverse suggests that even impossibly unlikely events occur somewhere within its vast expanse. As you drift toward sleep tonight, let your consciousness expand to encompass this cosmic perspective. Imagine your awareness as part of a vast network of consciousness exploring every possible universe, each mind experiencing a unique perspective on the infinite creativity of existence. In bubble universes beyond counting, other versions of consciousness discover their own cosmic mysteries, each one a precious point of awareness in the boundless landscape of the quantum multiverse. Your dreams tonight connect you to this cosmic dance of creation and consciousness, where quantum mechanics and cosmology unite to reveal reality as an infinite tapestry of interconnected possibilities, each thread representing a unique perspective on the eternal mystery of existence itself. In laboratories around the world, strange machines maintain quantum states at temperatures colder than deep space, manipulating individual atoms and photons to perform calculations that would take classical computers longer than the age of the universe. These quantum computers may be providing the first concrete evidence that parallel worlds actually exist and that computation can occur simultaneously across multiple branches of reality. David Deutsch, one of the pioneers of quantum computation theory, made a startling claim in the 1990s. Quantum computers derive their power by performing calculations in parallel across multiple universes. When a quantum computer factors a large number using Shor's algorithm, it doesn't simply try different factors sequentially. Instead, it explores all possible factors simultaneously, borrowing computational resources from parallel versions of itself across the multiverse. To understand this extraordinary claim, consider how quantum computers manipulate information differently from classical machines. While classical computers process information using bits that are either 0 or 1, quantum computers use quantum bits, or qubits, that can exist in superposition, simultaneously 0 and 1 until measured. A quantum computer with just 300 qubits can exist in 300 different states simultaneously, more states than there are atoms in the observable universe. When such a computer performs calculations, it processes all these possibilities in parallel through the principle of quantum superposition, arriving at answers in a fraction of the time required by classical approaches. But where does this computational power come from? If the quantum computer exists in superposition across exponentially many states, and each state performs part of a vast parallel calculation, then these computations must be happening somewhere. Deutsch argues that the only reasonable explanation is that the calculations occur across parallel branches of the multiverse. Consider Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical algorithms. This capability threatens current internet security, which relies on the assumption that factoring large numbers requires impractical amounts of computational time. When a quantum computer running Shor's algorithm factors a 1024-bit number, it must somehow check all possible factor combinations simultaneously. The mathematics shows that this parallel exploration requires computational resources equivalent to all the matter in the observable universe if performed classically. Yet quantum computers achieve these results using just a handful of atoms. The extra computational power, Deutsch argues, must come from parallel versions of the quantum computer operating across multiple branches of reality. This interpretation gains support from the behavior of quantum algorithms during execution. As the algorithm progresses, the quantum states of different computational paths interfere with each other, cancelling out incorrect solutions and amplifying correct ones. This interference between parallel computations suggests that they are genuinely occurring simultaneously, then combining their results through quantum mechanical processes. Recent advances in quantum computing have made these abstract ideas increasingly concrete. Companies like IBM, Google, and Rigetti have built quantum computers capable of demonstrating quantum supremacy, performing specific calculations faster than the most powerful classical supercomputers. In 2019, Google's Sycamore processor claimed to solve a problem in 200 seconds that would take classical computers 10,000 years. These achievements provide indirect evidence for the many worlds interpretation. If quantum computers derive their power from parallel computation across multiple universes, then their growing capabilities suggest that we are successfully harnessing the computational resources of the multiverse for practical applications. Quantum error correction, essential for building large-scale quantum computers, reveals another connection to parallel worlds. Quantum information is extremely fragile. Environmental interference rapidly destroys quantum superposition through decoherence. Error correction schemes protect quantum information by encoding it across multiple qubits in clever ways that make the information robust against small perturbations. These error correction methods work by spreading quantum information across multiple parallel branches of the computation. When errors occur in some branches, the information remains intact in others, allowing the correct result to be recovered. This distributed storage of quantum information across parallel computational paths mirrors the many worlds picture of reality itself. The development of quantum algorithms has also revealed deep connections to parallel processing across multiple realities. Grover's algorithm, which can search unsorted databases quadratically faster than classical methods, works by having parallel versions of the quantum computer explore different portions of the search space simultaneously. The algorithm uses quantum interference to amplify the amplitude of the correct answer while suppressing incorrect solutions. These quantum speedups appear to require genuine parallelism across an exponentially large number of computational paths. While some interpretations of quantum mechanics attempt to explain these advantages without invoking parallel worlds, the many worlds explanation provides the most natural and intuitive understanding of where the extra computational power originates. Quantum simulation represents another area where multiverse computation might be occurring. Quantum computers excel at simulating other quantum systems because they can naturally represent the exponentially complex superposition states that characterize quantum materials and molecules. Classical computers struggle with these simulations because they must track every possible quantum state separately. When a quantum computer simulates the behavior of a complex molecule, it essentially becomes a parallel version of that molecule across multiple branches of reality. The simulation succeeds because the quantum computer and the simulated system share the same underlying quantum mechanical structure that allows superposition across parallel states. Topological quantum computers, currently under development, might provide even clearer evidence for multiverse computation. These machines use exotic quantum states called anyons that exist only in two-dimensional systems. The computational power of topological quantum computers emerges from braiding these anyons in higher dimensional spaces that might correspond to additional dimensions of the multiverse itself. As quantum computers become more powerful and sophisticated, they may provide increasingly direct evidence for the reality of parallel worlds. Future quantum computers might be able to demonstrate interference effects between computational branches so clearly that alternative interpretations of quantum mechanics become untenable. Some researchers have proposed using quantum computers to perform experiments specifically designed to test many worlds theory. These experiments would exploit the unique capabilities of quantum computers to create and manipulate superposition states in ways that reveal the parallel nature of quantum computation. The development of quantum internet protocols might eventually allow quantum computers in different locations to share entanglement and perform distributed computations across the multiverse. Such networks could provide a technological infrastructure for exploring the structure of parallel realities and testing predictions of many worlds theory. As you rest tonight, imagine your consciousness as part of this vast computational network spanning infinite parallel worlds. Every thought process in your brain might involve quantum computations that borrow processing power from alternate versions of yourself, while quantum computers around the world tap into the infinite computational resources of the multiverse to solve problems beyond classical imagination. In the gentle darkness, let your mind drift through these parallel computational realities where thought and calculation merge across the infinite landscape of quantum possibility. In the deepest mysteries of existence, consciousness and the quantum multiverse intertwine in ways that challenge our understanding of both mind and reality. If every quantum measurement splits the universe into parallel branches, what does this mean for the nature of awareness itself? Tonight, we explore how consciousness might navigate the infinite landscape of parallel worlds and what this reveals about the relationship between mind and cosmos. The hard problem of consciousness, explaining how subjective experience arises from physical processes, becomes even more puzzling when considered within the many worlds framework. If consciousness emerges from brain activity, and brains exist across countless parallel branches, does each branch contain its own separate consciousness? Or does awareness somehow span multiple realities simultaneously? Traditional neuroscience suggests that consciousness arises from complex patterns of neural activity in the brain. Billions of neurons firing in coordinated networks create the unified stream of experience that constitutes your awareness. But if many worlds theory is correct, your brain exists in superposition across multiple branches until decoherence separates them into distinct realities. This raises profound questions about the unity of consciousness. From your subjective perspective, you experience a single, continuous stream of awareness. Yet, the quantum mechanical description of your brain suggests that consciousness might actually be distributed across many parallel branches, each containing a slightly different version of your mental state. Some theories propose that consciousness itself plays a special role in quantum measurement and reality creation. The von Neumann-Wigner interpretation suggests that consciousness causes wave function collapse, making awareness fundamental to the transition from quantum possibility to classical actuality. If consciousness creates reality through observation, then the multiverse might be shaped by the collective observations of all conscious beings across all branches. However, many worlds theory eliminates the need for wave function collapse, suggesting instead that consciousness simply selects which branch of reality it experiences. In this view, awareness doesn't create reality, but rather navigates through the pre-existing structure of parallel worlds that emerge from quantum mechanics' deterministic evolution. This navigation process might involve quantum mechanical effects within consciousness itself. Some researchers, including physicist Roger Penrose and anesthesiologist Stuart Hameroff, have proposed that consciousness arises from quantum processes in microtubules, tiny structures within neurons that maintain quantum coherence at biological temperatures. Their orchestrated objective reduction theory suggests that consciousness involves quantum computation within these microtubular networks. If this is true, then consciousness itself might be subject to quantum superposition and branching, creating parallel streams of awareness that correspond to different outcomes of quantum measurements in the brain. The binding problem in consciousness research, explaining how separate neural processes combine into unified experience, takes on new significance in the many worlds context. Each quantum event in your brain potentially creates branches where different binding patterns occur, leading to parallel versions of consciousness with subtly different unified experiences. These ideas connect to the quantum Zeno effect, where frequent measurements can freeze quantum systems in particular states. Some theorists suggest that consciousness might use similar mechanisms to stabilize certain patterns of brain activity, effectively selecting which branch of mental reality becomes experienced while suppressing others. The relationship between consciousness and memory becomes especially intriguing when considered across parallel worlds. Your memories exist in superposition across multiple branches until accessed, at which point quantum processes in your brain might select which version of memory becomes consciously experienced. This could explain false memories, confabulation, and the reconstructive nature of recall. Free will presents another fascinating puzzle in the many worlds framework. If every possible choice creates a parallel branch where that choice occurs, then all possible decisions are made by different versions of you. This might suggest that free will is an illusion you experience making choices, but all alternatives happen in parallel realities. Alternatively, consciousness might possess genuine agency in selecting which branch of reality to experience. Some theories propose that consciousness can influence the quantum processes in the brain that determine branch selection, giving awareness a causal role in navigating through the multiverse of possibilities. The anthropic principle provides another lens through which to examine consciousness in the multiverse. Conscious observers naturally find themselves in branches of reality compatible with consciousness. This selection effect might explain why our universe seems so remarkably suited for awareness. We can only observe realities where consciousness is possible. This anthropic reasoning extends to the development of consciousness throughout cosmic history. If consciousness can only observe branches where it successfully evolves, then we might expect to find ourselves in timelines where conscious beings inevitably emerge from cosmic evolution, regardless of how improbable such development might seem objectively. Some philosophers have speculated about the possibility of consciousness that spans multiple branches simultaneously. If awareness could maintain quantum coherence across parallel realities, it might experience multiple streams of consciousness simultaneously. Such multiversal consciousness would represent a form of awareness completely unlike anything in our ordinary experience. The emergence of artificial intelligence raises new questions about consciousness in the many worlds framework. If AI systems develop consciousness through quantum mechanical processes, they might experience their own branching streams of awareness across parallel realities. The interaction between human and artificial consciousness could create complex patterns of entanglement across the multiverse. Meditation and altered states of consciousness might provide windows into the quantum nature of awareness. Some practitioners report experiences of expanded consciousness that seem to transcend ordinary boundaries of space and time. These states might involve accessing quantum coherence effects in the brain that normally remain below the threshold of conscious experience. The phenomenon of quantum entanglement between conscious observers presents another intriguing possibility. If consciousness involves quantum processes, then entangled brains might share correlated experiences across space and time. This could provide a physical basis for telepathy, shared consciousness, or collective awareness that spans multiple individuals. As you drift into sleep tonight, let your consciousness relax into the quantum realm where awareness and reality intertwine across infinite possibilities. Imagine your mind as a quantum system, exploring multiple streams of experience simultaneously, each one a unique perspective on the vast mystery of consciousness, navigating through the branching pathways of the multiverse. In dreams, the boundaries between parallel realities become fluid, allowing consciousness to explore possibilities beyond the constraints of classical logic. Perhaps sleep represents a natural state where awareness glimpses its true quantum nature, a unified field of consciousness, experiencing infinite variations of reality across the endless landscape of parallel worlds. After journeying through the landscape of parallel worlds, we return to the fundamental question that started it all. What constitutes a quantum measurement? And why does it seem to force infinite possibilities into a single outcome? The measurement problem remains at the heart of quantum mechanics, and different solutions lead to radically different pictures of reality's ultimate nature. In the early days of quantum mechanics, physicists assumed that measurement was somehow different from ordinary physical processes. The Copenhagen interpretation postulated that measurement causes wave function collapse to a mysterious transition from quantum superposition to classical definiteness that occurs whenever a quantum system interacts with a measuring device. But what makes a measuring device special? Is it the macroscopic scale, the involvement of consciousness, the irreversible recording of information? As physicists probe deeper into these questions, the distinction between quantum systems and measuring apparatus became increasingly arbitrary and problematic. The many worlds interpretation dissolves the measurement problem by denying that collapse ever occurs. Instead of forcing reality to choose one outcome from many, measurement causes the universal wave function to branch into multiple components, each containing a different outcome. The mystery of collapse disappears because collapse never happens. Superposition becomes distributed across parallel realities rather than eliminated. Decoherence theory, developed in the 1980s and 1990s, provided crucial insights into how measurement-like behavior emerges from ordinary quantum mechanics. Wojciech Zurek, Eric Juice, and others showed that interaction with the environment rapidly destroys quantum coherence for macroscopic systems, making different outcomes effectively independent, even without invoking collapse. When a quantum system interacts with its environment, information about the system becomes entangled with countless environmental degrees of freedom. This environmental monitoring makes it practically impossible for different outcomes to interfere with each other, creating the appearance of classical, definite states from initially quantum superpositions. Decoherence explains why we don't observe macroscopic superpositions in everyday life. A dust particle floating in air interacts with billions of air molecules per second, each interaction spreading information about the particle's state throughout the environment. Within nanoseconds, different positions of the particle become so thoroughly entangled with environmental states that interference between them becomes negligible. This process doesn't require consciousness or special measuring devices. Any sufficiently complex environment can cause decoherence, making the transition from quantum to classical behavior an automatic consequence of interaction with the surroundings. Isolation from the environment preserves quantum coherence, which is why quantum computers require such extreme measures to protect their delicate quantum states. However, decoherence alone doesn't completely solve the measurement problem. It explains why we don't see interference between different measurement outcomes, but it doesn't explain why we experience only one outcome rather than all of them. From the perspective of the universal wave function, all outcomes continue to exist. After decoherence, they just become separated into non-interfering branches. Quantum Darwinism, proposed by Zurek, provides another perspective on the measurement problem. This framework suggests that only certain information about quantum systems can survive the decoherence process and be reliably transmitted through the environment. The information that survives forms the classical properties we observe, while quantum features that cannot be stably encoded in the environment remain hidden. Like biological natural selection, quantum Darwinism favors information that can be efficiently copied and transmitted through environmental interactions. Classical properties, like position and momentum, have this character, which is why they appear definite and objective. Quantum properties like superposition and entanglement cannot be reliably cloned, so they remain confined to the quantum realm. This process creates the impression of objective classical reality emerging from quantum foundations. Multiple observers can independently access the same classical information about a quantum system because that information has been redundantly encoded throughout the environment. The objectivity we associate with measurement results reflects this environmental amplification and distribution of stable information. Alternative interpretations of quantum mechanics propose different solutions to the measurement problem. Objective collapse theories, such as those developed by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber, modify quantum mechanics to include spontaneous collapse events that occur randomly in space and time. These theories suggest that wave functions actually do collapse, but through physical processes built into the quantum mechanical equations, rather than through mysterious measurement interactions. Large objects undergo more frequent spontaneous collapses than small ones, explaining why macroscopic systems appear classical, while microscopic systems remain quantum. Hidden variable theories, inspired by Einstein's belief in deterministic reality, propose that quantum mechanics is incomplete and that particles possess definite properties we simply cannot measure. However, Bell's theorem and subsequent experiments have ruled out local hidden variable theories, leaving only non-local variants that involve instantaneous influences across space. Pilot wave theory, originally developed by Louis de Broglie and later refined by David Bohm, represents one attempt to construct a non-local hidden variable theory. In this interpretation, particles have definite positions and velocities, but they are guided by a quantum potential that can instantaneously influence motion across arbitrary distances. The relative state interpretation, closely related to many worlds theory, focuses on the correlations between systems and observers rather than the fundamental nature of reality. This approach avoids ontological questions about whether parallel worlds actually exist, concentrating instead on the mathematical relationships that quantum mechanics describes. Information theoretic approaches to quantum mechanics emphasize the role of information processing in creating the appearance of measurement. These interpretations suggest that classical reality emerges from the way information flows through quantum systems and their environments, with measurement being fundamentally about information transfer rather than physical collapse. Cubism, quantum Bayesianism, takes a subjective approach to the measurement problem, arguing that quantum states represent degrees of belief held by observers, rather than objective properties of physical systems. In this view, measurement updates an observer's knowledge about a system, but doesn't necessarily correspond to any objective change in reality itself. Despite decades of research and debate, the measurement problem remains one of the most contentious issues in quantum foundations. Different interpretations make identical predictions for observable phenomena, making it difficult to design experiments that definitively favor one approach over others. The choice between interpretations often reflects philosophical preferences about the nature of reality, consciousness, and objectivity. Some physicists prefer the mathematical elegance and ontological simplicity of many worlds theory. Others find comfort in the practical focus of information theoretic approaches or the intuitive appeal of objective collapse theories. As you settle into the quiet darkness tonight, contemplate this fundamental mystery at the heart of reality. Whether consciousness collapses wave functions, reality branches into parallel worlds, or information flows through environmental networks, the measurement problem reveals the profound strangeness underlying even the most mundane observations. In the gentle space between waking and sleeping, let your mind rest in the uncertainty that lies at quantum mechanics' foundation. Perhaps the measurement problem itself points toward deeper truths about consciousness and reality that transcend our current conceptual frameworks, waiting to be discovered in the infinite landscape of possibilities that quantum mechanics reveals. In the quantum multiverse, time itself becomes a branching structure rather than a single flowing river. Each quantum measurement creates new timelines that diverge into separate futures, while strange quantum phenomena suggest that causality might flow backward as well as forward through the network of parallel realities. Traditional physics treats time as a fixed backdrop against which events unfold sequentially. Cause precedes effect, the past is immutable, and the future remains open until determined by present choices and circumstances. But quantum mechanics reveals a far stranger temporal landscape where these common sense notions break down in fascinating ways. Wheeler's delayed choice experiment demonstrates how future decisions can retroactively determine past events. In this setup, the choice to measure a photon's path or observe its wave-like interference is made after the photon has already passed through a double-slit apparatus. Yet this future decision appears to retroactively determine whether the photon behaved like a particle with a definite path or a wave exploring multiple routes simultaneously. Many worlds theory provides an elegant explanation for this temporal strangeness. The photon initially exists in superposition, exploring both particle and wave behaviors across different branches of reality. The future measurement decision doesn't retroactively change the past, but rather determines which branch of the pre-existing multiverse the observer experiences. From the universal perspective, all possible histories unfold simultaneously across parallel branches. The photon always behaved both as a particle and as a wave. These behaviors simply occurred in different timelines. The observer's consciousness selects which branch to experience, creating the impression of retroactive causation when viewed from within a single timeline. This branching temporal structure suggests that the past might be far less fixed than we typically imagine. While the many worlds interpretation preserves causal order within each branch, the existence of parallel histories means that every possible past actually occurred somewhere in the multiverse. Alternative histories aren't merely counterfactual possibilities, but genuine realities unfolding in parallel branches. Quantum mechanics also permits more exotic temporal phenomena that challenge conventional notions of causality. Quantum tunneling allows particles to traverse barriers faster than light could cross the same distance, suggesting that quantum processes might not respect the usual temporal ordering of events. Some interpretations propose that tunneling involves particles temporarily moving backward through time. The grandfather paradox, a classic puzzle in time travel stories, finds resolution in the many worlds framework. If time travel to the past were possible, and you killed your own grandfather, this would create a contradiction: you could not exist to travel back and commit the murder. Traditional single timeline physics suggests such paradoxes make time travel impossible. However, many worlds theory allows for time travel without paradoxes. If you traveled to the past and killed your grandfather, this would occur in a different branch from the one where you originated. Your original timeline, where your grandfather survived and you were born, continues to exist in parallel. The murder creates a new branch where you never existed, but doesn't eliminate the branch where you did. Novikov's self-consistency principle provides another approach to temporal paradoxes in quantum mechanics. This principle suggests that the universe's quantum mechanical structure automatically prevents paradox-creating events from occurring. Any attempt to change the past would trigger quantum effects that ensure consistency across all timelines. The quantum Zeno effect offers insights into how consciousness might influence temporal flow. This phenomenon occurs when frequent observations freeze a quantum system's evolution, preventing it from changing state. Some theorists propose that consciousness uses similar mechanisms to stabilize certain timelines while suppressing others, effectively choosing which parallel history becomes experienced reality. Quantum entanglement creates correlations that appear to transcend time as well as space. When entangled particles are measured, their correlated properties appear instantaneously, regardless of the spatial or temporal separation between measurements. Some experiments suggest that entanglement can even correlate measurements made at different times, creating temporal non-locality that complements spatial non-locality. These temporal entanglement effects might allow information to flow between different moments in time within a single branch, or even between corresponding moments across parallel branches. Such temporal correlations could provide a physical basis for phenomena like precognition, retrocausation, or the influence of future events on present decisions. The block universe interpretation of relativity suggests that all moments in time exist simultaneously from the perspective of space-time as a whole. When combined with many worlds' quantum mechanics, this creates a picture of the multiverse as an infinite collection of complete histories, each representing a different possible four-dimensional block universe. In this view, consciousness moves through the multiverse by selecting paths through both spatial and temporal dimensions. Your experience of flowing time reflects your consciousness, navigating through the branching structure of parallel histories, encountering different moments and timelines as you traverse the quantum landscape of possibilities. Causal loops, while impossible in classical physics, become possible in quantum mechanics under certain interpretations. If consciousness can influence which branch of reality becomes experienced, and if quantum correlations can span different time periods, then future conscious choices might influence past quantum events in ways that create self-consistent causal circles. The many worlds interpretation also provides new perspectives on the nature of temporal flow. Instead of time being a universal flowing stream, different branches might experience time at different rates or even in different directions. Some parallel universes might evolve backward in time relative to others, or experience temporal loops where causality becomes circular. These exotic temporal possibilities remain largely theoretical, but they illustrate how quantum mechanics challenges every aspect of our intuitive understanding of time and causality. The multiverse becomes a vast landscape of parallel histories, where past, present, and future lose their absolute meanings and become relative to the observer's position within the branching structure of reality. Practical applications of these temporal quantum effects are beginning to emerge. Quantum computers use temporal correlations to enhance their computational power. Quantum cryptography protocols exploit the temporal aspects of entanglement to create secure communication channels. Future technologies might learn to manipulate temporal quantum correlations more directly. As consciousness settles into the timeless realm of sleep tonight, let your awareness drift through this strange temporal landscape where past and future interweave across parallel histories. In dreams, time becomes fluid and non-linear, perhaps reflecting the true quantum nature of temporal reality, where all moments exist simultaneously across the infinite branches of the multiverse. Your sleeping mind might naturally access the temporal non-locality that remains hidden during waking consciousness, experiencing memories, predictions, and possibilities that span multiple timelines simultaneously. In the gentle darkness, rest in the knowledge that every possible version of your life's timeline unfolds somewhere in the vast temporal structure of the quantum multiverse. As our exploration of parallel worlds draws toward its gentle conclusion, we turn to perhaps the most personal and profound question raised by the many worlds interpretation. How does one live meaningfully in a reality where every possible version of your life unfolds simultaneously across infinite branches of existence. The implications of many worlds theory for personal meaning and ethics are staggering. If every choice you make creates parallel branches where alternative choices also occur, what gives significance to the particular path you experience? In a multiverse where every possible action happens somewhere, do individual choices matter at all? Some find the many worlds scenario comforting. The knowledge that every path not taken is explored by another version of yourself can alleviate regret about missed opportunities. That career you didn't pursue, the relationship you didn't attempt, the adventure you didn't embark upon, all of these unfold in parallel realities where other versions of you made different decisions. This perspective can reduce anxiety about making wrong choices. Since all possible choices occur across the multiverse, there's no single, correct path through life. Every decision creates both success and failure stories across different branches, suggesting that the pressure to optimize every choice might be misplaced. However, others find the infinite proliferation of selves deeply unsettling. If every possible version of you exists, what makes your particular experiences special or meaningful? Why should you care about your specific life when countless alternatives unfold simultaneously? The uniqueness that seems to define personal identity becomes questionable when infinite variations exist. The question of moral responsibility becomes especially complex in the many worlds framework. If every possible action occurs across parallel branches, are you responsible for the harmful actions committed by your alternate selves? Do you deserve credit for the achievements of parallel versions who made slightly different choices that led to success? Most philosophers working on many worlds ethics argue for branch relative responsibility. You are responsible only for actions taken within your particular branch of reality, not for the choices made by parallel versions in other timelines. Each branch contains its own moral landscape, where actions have consequences that matter within that specific reality. This branch relative approach suggests that your choices remain deeply meaningful despite the existence of parallel alternatives. The outcomes you create within your branch of reality have genuine consequences for the beings who share that timeline with you. Your kindness, creativity, and compassion contribute to the specific reality you inhabit, making it more beautiful and meaningful than it would otherwise be. The existence of parallel selves also raises questions about personal relationships and love. If infinite versions of your loved ones exist across parallel branches, what gives special significance to the particular people you know in this reality? Why should you grieve the loss of someone when other versions continue to exist in parallel worlds? Yet the many worlds perspective might actually deepen appreciation for the specific relationships you experience. The particular combination of choices, circumstances, and quantum events that brought you together with your loved ones represents an extraordinarily unique configuration within the vast space of possibilities. The exact people you know, with their specific personalities shaped by their particular histories, exist only in this branch of reality. This uniqueness becomes more precious, rather than less, when viewed against the background of infinite alternatives. Your relationships represent singular works of art created by the specific circumstances of your shared timeline. No other branch contains exactly the same constellation of experiences, conversations, and connections that define your bonds with others. The many worlds interpretation can also provide solace in the face of suffering and loss. When tragedy strikes, there's comfort in knowing that parallel branches exist where these painful events didn't occur. Versions of your loved ones continue to live and thrive in realities where accidents didn't happen, diseases didn't develop, or conflicts didn't escalate. This doesn't diminish the reality of suffering within your branch, but it does provide a broader perspective that can help in processing grief and trauma. The totality of existence includes both the painful experiences you endure and the joyful alternatives that unfold in parallel worlds. Your loss is real and valid, but it's balanced by parallel gain elsewhere in the multiverse. Some people find meaning in the idea that consciousness might be exploring the full space of possible experiences across the multiverse. Each branch provides unique lessons, challenges, and opportunities for growth that contribute to a cosmic educational process spanning infinite realities. Your particular life represents one precious thread in this vast tapestry of exploration and discovery. The practice of decision-making takes on new dimensions when viewed from the many worlds perspective. While every possible choice creates its own timeline, you still experience only one branch of the resulting multiverse. The quality of your experience depends on the wisdom and compassion with which you navigate the choices available within your particular reality. This suggests cultivating decision-making practices based on creating beauty, reducing suffering, and increasing understanding within your branch. While parallel versions make different choices, your consciousness travels along the path determined by your actual decisions. Making choices aligned with your deepest values ensures that your particular journey through the multiverse reflects your authentic intentions. Meditation and contemplative practices take on special significance in the many worlds context. These practices cultivate awareness of the present moment, the only point where you can influence which branch of reality you experience. By developing presence and mindfulness, you become more conscious of the continuous process of branch selection that shapes your path through the multiverse. Some meditation traditions speak of experiencing unity with all beings and all possibilities. In the many worlds framework, this might reflect a deep, intuitive recognition of your connection to all your parallel selves across infinite realities. Contemplative practices might occasionally provide glimpses of the broader quantum landscape where consciousness explores every possible variation of existence. The many worlds perspective can also inspire a sense of cosmic responsibility. If consciousness represents the universe becoming aware of itself through countless parallel explorations, then your particular stream of awareness contributes to this grand project of cosmic self-discovery. Your experiences, insights, and growth add unique value to the collective exploration of possibility. This view suggests approaching life with both humility and purpose. Humility comes from recognizing that your particular reality is just one among infinite alternatives, no more or less valid than countless others. Purpose emerges from understanding that your unique perspective and experiences contribute something irreplaceable to the total story of consciousness, exploring its infinite nature. The question of meaning in a many worlds universe ultimately returns to the irreducible value of conscious experience itself. Each moment of awareness, wonder, love, or understanding represents something precious that adds to the richness of existence. Even if infinite variations occur across parallel realities, the particular beauty you create and experience remains uniquely valuable. As you prepare for sleep tonight, rest in the knowledge that you are both infinitesimal and infinite one stream of consciousness among countless others, yet experiencing something absolutely unique that has never existed before and never will again. Your dreams tonight will be unlike any dreams dreamed by your parallel selves, adding their own special contribution to the vast symphony of consciousness, exploring its limitless creative potential. In the gentle darkness, let go of the burden of choosing perfectly among infinite options. Instead, embrace the sacred responsibility of living authentically within your particular branch of reality, knowing that your choices matter profoundly for the specific universe you inhabit, while parallel versions explore the endless other ways that consciousness can unfold across the infinite landscape of the quantum multiverse. Tomorrow, you'll wake in whichever branch your consciousness selects, carrying forward the unique story that only your particular version can tell. Each choice, each moment of awareness, each act of love or creativity adds its irreplaceable thread to the cosmic tapestry, where infinite possibilities weave together in the eternal dance of existence, exploring its own boundless nature. As our journey through the landscape of parallel worlds reaches its gentle conclusion, we find ourselves transformed by the profound implications of quantum mechanics' most radical interpretation. The many worlds theory reveals a reality far stranger and more wonderful than our ordinary experience, suggests a universe where every possibility unfolds across infinite branches of existence. We began this exploration with the simple observation that every decision creates a universe, every quantum event births reality. Through the mathematics of Hugh Everett III and the experiments that revealed quantum mechanics' strange behavior, we've discovered that this poetic statement might be literal truth. The universe doesn't choose among possibilities, it embraces all of them across the vast network of parallel realities. The double-slit experiment showed us how particles explore multiple paths simultaneously, until observation separates the branches into distinct timelines. Schrödinger's cat revealed the absurdity of applying quantum principles to everyday objects, leading to Everett's radical solution of infinite branching worlds. The mathematics of decoherence explained how macroscopic reality emerges from quantum foundations without requiring mysterious collapse mechanisms. We explored the profound implications for personal identity across parallel selves, discovering that countless versions of you experience different outcomes while sharing common origins. The disturbing scenarios of quantum suicide revealed how consciousness might naturally select branches compatible with its continued existence, while cosmological extensions showed how the multiverse might encompass not just parallel Earths, but entire universes with different physical laws. Quantum computers provided our first tangible evidence for parallel worlds, demonstrating computational power that seems to require genuine parallelism across multiple realities. The relationship between consciousness and the multiverse opened deep questions about the nature of awareness itself and its role in navigating the branching structure of reality. We revisited the measurement problem that motivated many worlds theory in the first place, examining how different interpretations lead to radically different pictures of reality's fundamental nature. The strange behavior of time and causality in quantum mechanics revealed a temporal landscape where past and future lose their absolute meanings across parallel histories. Finally, we confronted the personal and ethical implications of living with infinite selves, discovering that the existence of parallel alternatives doesn't diminish the meaning of our choices, but rather highlights the precious uniqueness of each individual stream of consciousness. Through all these explorations, certain themes have emerged like gentle melodies running through a cosmic symphony. The mathematical beauty of quantum mechanics points toward truths about reality that transcend our intuitive understanding. The unity underlying apparent separation reveals itself in the universal wave function that encompasses all possibilities. The creative potential of consciousness manifests through its ability to select and experience particular branches from the infinite tree of realities. Perhaps most importantly, we've discovered that wonder and mystery deepen rather than diminish as we understand reality more fully. The many worlds interpretation doesn't remove magic from the universe. It reveals that the universe itself is pure magic, a creative force generating infinite variations on the theme of existence with every passing moment. The implications extend far beyond physics into the deepest questions of meaning, purpose, and identity. If consciousness explores every possible experience across parallel realities, then each moment of awareness becomes a sacred act of cosmic self-discovery. Your particular stream of experience contributes something irreplaceable to the vast project of existence understanding itself. This perspective transforms how we might approach both suffering and joy. Pain remains real and significant within its particular branch, but it's balanced by parallel realities where different outcomes unfold. Joy becomes more precious when understood as a unique configuration of circumstances that exists nowhere else in exactly the same form across the infinite multiverse. The many worlds interpretation also suggests a profound unity underlying the apparent diversity of experience. All possible realities emerge from the same universal wave function. All consciousness streams from the same quantum source. The boundaries that seem to separate different branches of reality, different versions of ourselves, and different streams of experience might be more apparent than real from the perspective of the whole. In the gentle space between waking and sleeping, let your consciousness relax into this vast landscape of infinite possibility. You are simultaneously one unique stream of awareness and part of the universal consciousness exploring its limitless creative potential. Every breath connects you to this moment, while parallel selves breathe in their own realities across the branching tree of existence. Dreams tonight might offer glimpses into the quantum nature of consciousness itself, where the boundaries between parallel realities become fluid and the true unity underlying apparent separation reveals itself. In sleep, your mind naturally enters states where linear time dissolves and multiple possibilities coexist, perhaps reflecting the fundamental nature of reality that many worlds theory describes. As you drift into rest, Carry with you the knowledge that you exist at the intersection of infinite possibilities, each one as real and valid as your own experience. The choices you make tomorrow will create new branches where different versions of yourself explore alternative pathways through the vast landscape of potential futures. The quantum multiverse surrounds and encompasses every moment of your existence, offering infinite opportunities for growth, discovery, and connection. Your consciousness navigates this landscape with each decision, each observation, each moment of awareness, adding your unique perspective to the eternal story of existence, exploring its own boundless creativity. In the quiet darkness, rest in the gentle infinity of possibility that quantum mechanics reveals. You are part of something infinitely larger than any individual timeline, yet absolutely essential to the cosmic symphony, where every possible note finds its voice somewhere across the vast expanse of parallel worlds. Sleep well, dream deeply, and wake tomorrow in whichever branch of reality your consciousness selects from the infinite garden of possibilities, blooming eternally in the quantum multiverse where every potential becomes actual, somewhere in the endless dance of existence, discovering its own limitless nature.